We're going to be using matrices to help us solve systems of equations, but before we do that, I want to take a look just at some basic definitions. First of all, what is a matrix? It's simply an array, which is things with rows and columns, array of numbers called elements, and we denote those elements as A sub ij, where that I, that first subscript, is the row that the element is in, and that j, the second subscript, is the column that it's in. The order of a matrix is denoted m by n, where m stands for the number of rows and n stands for the number of columns. When you work with matrices, you know a lot of things are done row, column, so it's always kind of that way. So here I've got this matrix, and I denote it with these little squared off brackets. You don't do straight lines, that means something else, so squared off little brackets. And it's got 2, 4, 1 in the top row, 3, 0, 5 in the bottom row. So this would be, as I've noted here, a 2 by 3 matrix. 2 rows horizontal and 3 columns vertical. Now, what would A sub 1, 2 be? That's row and column, so the first row, second element would be 4. What if I switch that? A sub 2, 1. That would be second row in the first entry. So that would be the 3 over here, right? Second row, first one. A sub 2, 3, second row, third entry. Yep, that's 5. But if you switch it this time, A sub 3, 2, there is no third row, so this is not applicable. It's not an answer. There's nothing we can answer there. All right, so order is really important when it comes to matrices. Something called an augmented matrix is what we're going to be using with systems of equations, and that's just simply a matrix whose elements, those rows and columns, are the coefficients and constants from a system of equations. So I've got a first example here, 2 nice linear equations, and all I'm going to do is I'm going to take all those numbers, coefficients, and put them as my first row, so the 1 that's assumed, the negative 2, include the sign, and then the 5. The second row, same thing, the 4, the 1, and the negative 7 become the second row. Now, one thing we usually do with augmented matrices is we draw a vertical line between the variable coefficients and that constant column at the end. So the first column, those are all x coefficients. Second column, those are all y coefficients. And the last column, that's going to be just my constants or my plain numbers. So you'll notice that when I come to the second equation, we've got a little work to do before I can get my augmented matrix. This first equation is not in the right order. We need everything lined up nicely. So we're going to bring the 4x over, subtract it, and make it negative 4x plus y equals 2. Then everything's lined up neatly, and I can take my coefficients, negative 4, 1, and 2, and 3, negative 1, and 5 for that second one. Now, what about going the other direction? What if we're given this giant matrix here and told to come up with a system of equations? Well, if I've got 3 columns here on the variable side, that probably means I'm dealing with x, y, and z. If I had 4 columns on the variable sides, that'd probably be w, x, y, and z. Okay, you can make them whatever you want, but those are the ones we're probably going to usually use on this textbook. So if this is my x, this is my y, my z, that vertical line's where we put the equals, and this is my constant, the first row would become 3x plus a y, we usually don't put 1, plus 2z equals a 4. Now come down to the second row, that's going to be 2x minus 4y, and there are no z's, there's a 0 there, so we just leave that part blank, equals 5. And then the last one, the 2x plus 3y minus 4z is going to equal 8.